Welcome everyone to this Rump session of the COMSOC video seminar. We have a jam-packed program with 12 talks. Each talk will be 5 minutes. And after each half of 6 talks, we'll have a 10-minute discussion session in breakout rooms where you can choose your own breakout room and which speaker to talk to. All the speakers are here. And so I think we can get started. Our first speaker is Vishwa Prakash, about fair and efficient completion of indivisible goods.
Hi. Can you,
Yep.
Okay. Hello, everyone. I'm Vishwa Prakash. I'm a PhD student at the Chennai Mathematical Institute. I'm here to present our work on fair and efficient completion of indivisible items. So this is a joint work with Ayumi Igarashi from University of Tokyo and Rohit Vesh from IIT Delhi. Yeah. Here is a photo of the last will of Benjamin Franklin. So why I show this is this is a summary of the things that he mentions in his last will. So he says that the land in Nevada should go to his son. He says the King Francis picture should go to his daughter, and his son-in-law must get his musical instruments, and so on. So this is a typical will statement that one would write, where there are some pre-allocated items. So we consider the model of frozen allocation, where let's say this is a set of all items. But some items, such as the printing machine, musical items, or the books, are pre-allocated, and you cannot change these items. They are frozen for these agents. So the task now is to allocate the remaining items to these agents such a way that the final allocation is fair and efficient. So the question is, given a set of frozen unassigned items, find a fair and efficient completion. So we argue that this is the situation in many real-life settings. For example, course allocations to students, but some students might have mandatory courses, some subset of courses that they must do. So, or even if you consider the house chore allocation between couples, there are some fixed chores. For example, breastfeeding, always done by the mother. So, or even in divorce settlements, where the court following the court order, some assets might be pre-assigned to some of the parties. So motivated by these examples, so we consider the problem both under the existence as well as the computational complexity of finding one if it exists. So to quickly see the existence, here is an example. If we say that the diamond, two agents with identical values, everyone values the diamond more than candy. So if we just freeze diamond and candy to one agent, we can quickly verify that there is no EF1 completion for this example. However, we know that EF1 allocation always exists for n agents, even for general monotone valuations due to Lipton et al. So similar examples can be constructed to show that prop1 completion also does not always exist, even for two agents under identical valuation. However, we know that prop1 exists for even subadditive valuations. So is the case with alpha MMS completion for any alpha for agents with additive valuations. But we know that the standard problem has 3/4 MMS completion always known to exist for n agents. So this is the picture for existence. So we also consider the computational complexity of finding such allocation. If we limit ourselves to binary additive valuations, we show that there's a stark difference when it comes to NV-based fairness notions, such as EF1, even if you ask without the Pareto optimality or with the Pareto optimality, finding such NV-free completion of a given frozen allocation is NP complete. However, share-based notions such as the prop1 and MMS, even finding along with Pareto optimality, remains to be polytime. So we also consider the same setting under lexicographic preferences. We know that EF1 and prop1, they all exist and can be found in polynomial time. However, the NV-free notion again remains to be NP-complete, but the share-based notion, even with polynomial time, even with the Pareto optimality, can be computed in polynomial time. So, but if we consider the general additive valuations, we show that all the properties EF1, Prop1, MMS, with or without Pareto optimality, except for MMS plus PO, is NP hard and NP complete. We show reductions from various known NP complete problems. So in comparison, EF1 and Prop1 is known to be in polytime, however, and EF1 plus PO is known to be in pseudo polynomial time. So this is the landscape of completion of EF1, completion of fair and efficient completion of allocations. Thank you.
Thank you. Very well timed. You can discuss later in the breakout room or in the chat. Our second speaker is Hadi Hosseini.
Okay, so let me see how I can share my screen. I'm going to share the full screen because I'm going to go back and forth between the slides and a live demo. Okay. All right, so let me know if you see the screen and what you see in the screen.
I see a slide presentation.
Yes.
Okay, perfect. All right, so hi, everybody. My name is Hadi Hosseini. I'm here today to talk about our matching platform. We call it MatchU.ai. It's actually a live platform that we have been working on this since 2020. So this is not really new platform, as in contrast to what Dominic was mentioning in the emails. But I have good news because we are working on something else that I'm going to give you a little bit of a sneak peek towards the end of this. So what is MatchU.ai? So when we started this kind of MatchU.ai, we kind of had this vision of developing different types of allocations and matching algorithms that are available, and many of us are familiar with those, and allow people to use this in their everyday life for their decision making, right? So imagine you're deciding what type of projects you want to work on, and you kind of care about, you have some preferences over these projects, and you want to make a decision with your friends, right? So one of the key aspects of this was this interactive design. We wanted to make sure that people can actually understand and see the steps of the algorithm. So what we started with was the vision, that was the initial vision for MatchU.ai. But interestingly, as time kind of passed, we realized that most people are actually more interested in learning the algorithm and using this MatchU.ai as an educational platform, right? To learn about these different type of algorithms. And also, we've received a bunch of emails from different people around the world talking about how they're using this in their classrooms. And they're using in their undergraduate or graduate classes where they're talking about matching because it gives them a way to visualize and step-by-step analyze different type of algorithms. So this is kind of like a broad idea behind MatchU. And then we started more kind of focusing on that aspect, the aspect of education and pedagogy, and use it as a pedagogical tool. So as I mentioned, so it has been used over, we've had many, many users over the past few years from more than 95 countries. And if you look at the website, it talks about different types of allocation or matching algorithms. Some of them are kind of focused on two-sided matchings or matching with two-sided preferences. Some of them are focused on one-sided matchings, but randomized solutions or randomized or assignment mechanisms. And of course, we also have matching with endowments. And interestingly, at some point, we kind of got interested to see if actually this is going to help people learn more about matching, right? So we kind of see that if this type of platform is going to be better than maybe traditional flat platform for learning these algorithms, for instance, looking at videos or reading lecture notes. So we actually done some studies that if you're interested, I put the kind of reference of the paper that we published at 6C in 2023 about our findings. So the reason I'm here, I want to kind of encourage all of you to use this platform and also tell you that I want the community's feedback to let us know what you want to see in this matching platform, right? And in the future. And as a sneak peek, I wanted to tell you that we are working on a different platform now. It's not, I haven't really put it, I'm not going to too much advertise it too much because it's not really ready to go out. But the idea here is to provide explainable matchings, right? So we will be able to provide explanation for the data that you're providing to these matching algorithms, and also give you solutions that you can see and you can manipulate, right, as you go. Okay, I'm going to stop here and kind of show you maybe some examples from MatchU. So if you go on the website, I hope you're seeing my webpage or the webpage of MatchU. You can actually look at any of these algorithms. For instance, we can look at the probabilistic serial rule, which is a randomized algorithm. There are different tabs here. One is to learn about different aspects, or if you're interested in reading papers. There's also interact. You can choose, let's say, 5 agents. You can populate preferences. You can also change the preferences as you want. And on top of that, then you can run the algorithm, right? So it actually starts running the algorithm, and step by step, this is kind of showing you the simultaneous eating algorithms that many of you may be familiar with, right? So at the end of this step, you're going to have some probabilistic allocations, right? So that you can see for each agent. By the way, you have like tools that you can back and forth. You can go back and forth between these steps, and you can also generate some samples. Right? So if you want to generate some samples, because these are random, you want to sample at the end, you can generate different types of samples, right? I was hoping to also show you another example, which is the house allocation, but it looks like Dominic's thing is catching me, so I'm just going to go very quickly. So this is the famous TTC algorithm that you can see completely visualized, and step by step, it shows you how the houses are being transferred. Okay, I'm going to stop here.
Thank you very much. The third talk is by Tomasz Wons.
Can you see my screen?
Yes.
Perfect. Okay, so hello everyone, I'm Tomasz Wons, and I would like to tell you about the squared Kemeny rule for averaging rankings, which we kind of rediscovered with Patrick Lederer, Dominic Peters, and myself. So let me start with the motivational example. So imagine that you are going to a conference and you're looking for some accommodation. So then you can go to the website like booking.com or Expedia or anything else similar. And there you can see all of these possible accommodation options, and you can sort them according to their price, for example, or to the distance to the conference center. And you will see this kind of different rankings. But actually, you are not interested in any of these rankings, but ideally you would like to somehow combine them. And let's say that you are tight on budget, so you put like more weight on the price vector, let's say like a 75% weight on the price, and 25% on the distance ranking. So you can imagine that on the website, there will be kind of like a slider that will allow you to specify your preferences. And then we would like to somehow aggregate those rankings together. And the most standard computational social choice tool to do that would be a Kemeny rule that is defined as the ranking that minimizes weighted average swap distance to the input rankings. But since this rule is majoritarian, in this case, it will just output the ranking that is identical to the price rank. And actually, some other standard rules like Borda or STV would also, in this example, do exactly the same. And this is not really what we wanted. Yes, we wanted to somehow combine both of these rankings, not simply output the one for which we put more than 50% weight. So how we can do it in a more proportional way, and what even proportionality would mean in this setting. So actually, if we just have 2 rankings, there is quite natural notion of proportionality here. So you can observe that these 2 rankings, actually, they differ on 8 swaps of consecutive alternatives. Yes, we have to do 8 swaps to change one of these rankings into the other. Or in other words, we can say that they disagree on ordering of 8 pairs of alternatives. So one idea of what the proportional output would be here is to say that since we put 3 times more weight on price ranking than on the distance ranking, then the output should be actually 3 times closer to the price ranking than to the distance ranking. So we can say something like this, and we can generalize this for any situation when we have exactly two rankings with some weights, that the output should be in this proportional distance between them according to the swap distance. And we formalize it in the form of the axiom that we call two-ranking proportionality. So now the question is, what kind of rule would satisfy this axiom? Like I said before, it will not be Kemeny rule, defined as this weighted average, the ranking that minimizes weighted average swap distance. And actually, this Kemeny rule in the original paper by Kemeny was called by him the median rule, because he also introduced in the same paper another rule that he called the mean rule, which is defined in exactly the same way, but instead of taking just swap distance, we take swap distance squared. And while this first rule, the median rule, has been extensively studied in the literature, and now it's simply called the Kemeny rule, the second rule, the mean rule, was actually not really studied anymore after that. But it turns out it satisfied this two-ranking proportionality that I was mentioning. So we thought that this is actually some gap in the literature that we can fill, and we called this mean rule this squared Kemeny rule, because it's just like Kemeny, but so in our paper we take a look at this rule. We study it axiomatically. We provide more or less. We provided in particular we provided axiomatic characterization using this two-ranking proportionality. So we say that it's the only rule that will satisfy two-ranking proportionality and some other standard axioms. We also show that it satisfies some more general proportionality guarantees. We discuss its computation. And we also conduct some experiments producing these cool pictures that I have no time to talk about because of the timer. But the discussion is far from over. So definitely more can be said about squared Kemeny, and also probably there are some other potentially interesting rules for proportional ranking aggregation, maybe inspired by multi-winner voting or by issue voting or something else. And if you like to know more, there is an archive version of our paper, so take a look, and thank you for listening.
Thank you very much. Bang on time. Our fourth talk is by Sarfaraz Equbal. Oh, no, it's by Matthieu Hervouin. Sorry. Skipping ahead here.
Yeah, sorry, I thought I skipped it. So, hi everyone, I'm Matthieu Hervouin, and I'm presenting a project I'm working on with Jan Mali and with Sanchez Fernandez. So it's not something that we have finished or anything, it's still a project, an ongoing project. So the goal is to work on participatory budgeting and committee election when considering trichotomous ballots. Sorry. Yeah. So usually in participatory budgeting, the most common in committee election, we mostly use approval ballots or cardinal ballots or ranking ballots, and we suppose that every project or candidate is a bit positive, is good. So, and this is actually not the case. So here is an example of a project that's created like huge protests in France, and there are also projects that are selected from PB that creates that not really protest, but that creates negative feeling. So we will argue that we need to have participatory budgeting systems for trichotomous ballots. So that's a good idea, yes. But then for participatory budgeting and committee election, we need to have something that is proportional usually, or we want to have this. And then how can we define this? So for positive proportionality, when you want to have some candidates and you agree on some candidates being selected, then it's quite, we will do it like a bit like for approval ballots. If you represent 10% of the population, you should have 10% of the budget. But for negative proportionality, it's not really clear. There are basically two options. Either you can decide on 10% of the project or 10% of the candidates that will be eliminated, or you should get that at least 10% of the projects that are selected are not bad for you. And also, it's a bit more hard to define it for participatory budgeting. So for now, we are focusing on community elections. The bad news is if we want to have the really classic JR axioms, so justified representation axioms from approval, some for approval-based committee election, then both of them are incompatible. So this is an example with committee size 2, where like it's committee election. If there is one voter that is for that is for project 1 and the organ is against project 1 and they don't care about project 2, then voter 1 is represents half of the voters, so it should get half of the budget, and he cannot get it because it's also the case for voter 2 that represent half of the voters, so he should decide on half of the budget. For the same reason, price stability is not really adapted to this setting. So the first option that we tried to do was to work on an existing axiom that is about proportionality for like a more general framework than committee election and participatory budgeting. And it's basically, so it's not just for trichotomous election, but it can be applied to trichotomous election. And in trichotomous election, it's a bit like worst case scenario. So we consider as if every other voter were against the candidate that you support. And in this example, you have two groups of voters, 1 and 3, that agree on selecting P2 and deleting P3, and 2 and 4 agree on selecting P1. So if we are proportional, we should have that P1 and P2 are selected, or at least P1 is selected. But according to Mazaric axioms, it should not be selected here, so it's a bit bad. I mean, so the axioms actually works, but it's not like as good as what we would want. And so our goal is to define an axiom that is specific to trichotomous ballots, and that may be better for trichotomous ballots. And the idea is that when you select a project, you need to compensate the opponents of the project. And on this we have this example here where, according to Mazaric axiom, we have the three first candidates that agree, the three first voters that agree on like basically selecting any candidate, and the last one is against any candidate. So according to these axioms, if the number of projects is really high compared to the committee size, then basically the three first voter will have a K candidates that are selected where K is the committee size. And we will actually want that there are not K candidates that are selected, but less than this. And this is why we managed to define an axiom that is a bit based on AGR plus that was introduced by Yannick Peters and Marcus Brill. And yes, that's it for now, because I'm finished about the time. So if you have any question about this and you want to discuss about how to apply it to participatory budgeting, just ask us, please.
Thank you very much. Okay. Sarfaraz, now it's your turn.
Thank you. Hello all, I'm Sarfaraz Iqbal, PhD student from IIT Bombay, and this work is done with collaboration with Rohit Gujar, Yatharth Kumar, Swarup Nath, and Rohit Vyas. From some of them are IIT Delhi and some are from IIT Bombay. First of all, I wanted to thanks for giving me the opportunity to talk about my work. So the task is like fair allocation of indivisible chore. For example, if we have like household chores and we wanted to divide it with the two agents, then what are the constraints we have? The first constraint is like individual chores, so we cannot divide a chore between the two agents. Like two agents cannot do same task, and then each task have like associated weight. That weight is a like kind of preference of that agent, and then because each task have a dedicated time, so one agent can do a task, a single task at a time, and each task or each chore have like a start time and finish time. So when the task is start, you have to start performing that task, and then at the finish of time you have to finish it. And for the fairness, we consider the infiniteness, or like infiniteness for one chore or any chore. And for efficiency, we are taking on like a completeness, or we are considering the maximality. Here, what is the maximality for this? If you have a fair allocation, and if you have fair allocation and one task is unallocated, so without the violate the feasibility, you cannot assign a task to other. If that allocation is kind of that, then we call this allocation as maximality. So our goal is to find a fair and efficient scheduling for indivisible chores. So the in results we have like first we able to prove that there is no better than the EF1 and maximality. Like anything such as like EFX and maximality or EF1 and completeness is not possible. So we have to settle with the EF1 and maximality, and then further we able to give an algorithms that for the EF for two agent under the monotone evaluation, and when the conflict graph of the chores is an arbitrary interval graph, we have a polynomial algorithm. So, what is the idea of that algorithms? Like, algorithm will work when, like, first we will start from any arbitrary maximal schedule that may not be the EF1, but but then we revert the assignment one by one in a small part, and we like then we wanted to reach an assignment that is completely opposite the assignment with respect to the first assignment. Like we swap all the bundles of the assignment, and what we are hoping, like if we will do like small changes in every assignment, every reward, then we will hit an assignment in between this, that is EF1 and maximum. So if we will take an example of six chore, that is like the conflict graph of this chores is a path graph, simple path graph, and we wanted to divide it within two red and blue agents. And if we start from an arbitrary assignment, it is like alternate red and blue, and in each step we are like just alternating the assignment in very small invert the assignment in very small part. Then like one by one, if we are doing that, and we are reaching an assignment that is like completely opposite of first assignment, like in this example x1 and x6 is completely opposite, where the all the chores that is assigned to red is assigned to blue now, and blue in assignment 6. If we are doing so, then we have like we able to prove that if you are doing this, then in between from 1 to 6 we must have an assignment that is EF1 and maximal. So further what we do, like we able to extend this same idea for any arbitrary conflict graph for the two agents only. So and then for arbitrary number of agents under some restricted evaluation setting, we also gave some algorithms for some different class of conflict graphs. But the interesting open problem is kind of EF1 and maximal shooting for more than two agents is currently not solved. So we have open problem for more than two agent, three or more agent. And further, like we can look into the different kind of fairness notion, like kind of proportionality, equitability, or max min phase. That's all. Thank you.
Thank you very much. And the last talk in this half of the session is by Vincent Conitzer about social choice for AI alignment.
Thank you, Dominic. Can you see and hear?
Yes.
Great. Well, thank you, Dominic, and everybody for keeping this going. I'm sorry that I haven't been able to participate in the seminar series as much as I would have liked to, but I'm really happy to see it continuing. So my quick talk here is not so much about technical results as it is more a call for action. In particular for us as the computational social choice community to get more involved in what is often called AI alignment. What does that mean? It means different things to different people. Roughly, it means something like getting AI systems to do what it is that we really want them to do. So that's very broad, but it finds specific expression already in things like large language models, such as ChatGPT. We want them to behave in particular ways. For example, we want them not to output toxic content. But what exactly does that mean, toxic content, right? We will disagree on our definition of toxic content. And so that's why this is a good question for social choice. And it leads to lots of good technical questions as well, because the ways in which we get these systems to behave better, to not output toxic content, for example, vary. You could do it by fine-tuning the model or by prompting. And so that leads, I think, to lots of interesting technical questions. So that's the very quick overview of what I'm going to do. We started this with a workshop last December, I think, in Berkeley, organized with Jobst and Wes. And from that, actually, we developed a position paper that will appear in ICML that you can see here. Again, this is a position paper, so it says that there's work that we need to do here. And then next, I want to advertise that we will have a workshop on this at ECAI this year. The deadline you can see down here is coming up very shortly. And so I hope you will submit. In particular, it's not necessary that your paper is exactly on this topic. After all, the whole point is that we think this is an understudied area. So if you have a computational social choice paper that you think you can link in some way, or you think you have something interesting to say at this workshop, please do submit, because we don't want to have no submissions precisely because it's a new topic. Okay, in the time that remains, I'll very quickly give a little bit of insight, hopefully, into what these problems are like. So here's an example where at some point, I think last year, ChatGPT started to allow you to generate images. So it was integrated with DALL-E. And the way that this works is you can ask ChatGPT for pictures of some sort, and then it actually goes and it formulates a prompt to DALL-E, which is an image generator. And so here's an example that you can see where I asked for, this was actually during a small meeting that we had with my group, and I wanted it to generate a picture that would somehow resemble the meeting. It generated a couple of pictures. We can critique lots of elements of the picture, but what I want to focus on here is that if you look at the speakers, I would say they're a remarkably diverse bunch, right, compared to maybe computer science in general. And it's interesting that there's a reason for that, because you can actually find out something about the prompts that ChatGPT gave to DALL-E, because they're hidden in the file names of the pictures. And in fact, if you look at the file names, they reveal that the prompt to DALL-E had very specific instructions, for example, saying that it should be a man of African descent that is presenting to the group. Notice that I didn't say anything about that. It decided on its own to include that in the prompt. I presented this a while ago, and then one of my colleagues, Derek Leben, said, oh, I know why that is happening, because I still know how to get to what's sometimes called the meta prompt. So ChatGPT itself has been prompted to behave in a particular way. And interestingly, you can still get ChatGPT to reveal these prompts to you, at least at the time you could. And Derek was smart enough to actually keep around this prompt. So this is OpenAI had given ChatGPT the following prompt, and this is just part of it, but it's the relevant part where it says actually, well, when you make a prompt to DALL-E, you should pay attention to diversity, and in particular, you should use all possible different descents of people with equal probability, which I still think is kind of a funny way to phrase it. But that's what caused these prompts to care about diversity. In fact, then I tried it myself, and by that point in January, a month later, it had completely changed. They got more worried about copyright and other things. So then I tried a couple more things. I tried saying, well, what about a bunch of scientists hanging out? What about a bunch of basketball players hanging out? You can see the pictures here. So you can kind of see that, well, the prompt really did have an effect. Okay, there's much more to say. It's not all about prompting. It's also, by the way, we also have a blog post on this. But there's also this methodology called RLHF that you might have heard about, constitutional AI. There are many different ways to get these systems to behave. And I think all of them correspond to interesting and different computational social choice questions. So I think there's a ton left to do. I'll stop there.
Thanks very much, Vince, and all of our first 6 speakers. We are now going to go into breakout rooms. You can select your own breakout room to discuss with the speakers, and I believe it's also possible to change breakout rooms if you have several speakers you want to talk to, and we'll see each other again in about 10 minutes. Before we start going back to the talks, we have a few announcements to make. And Bill Swicker has the first announcement.
Yes, I'm very pleased to announce that the 10th International Workshop on Computational Social Choice will take place at the Technical University of Vienna in Austria in September of 2025 under the leadership of Jihua Chen and Peter Biro. An email announcement will be out soon with more specific dates, and I invite all of you to consider coming to Vienna next year.
Thank you very much. From me, I'm announcing that there will be a workshop on future directions in social choice happening at EC 2024. So if you are planning to come and you have something that you want to present, please feel free to submit a paper. And our next seminar in this series will happen next month on the 13th of June, when you will hear from Theo de la Mazur and Jean Lenné. Okay, let's get back to talks. The next talk is by Paritosh Verma. Please go ahead.
I hope the screen is visible.
It is.
So I'm Paritosh Verma, and I'll be presenting our work, which is titled Fairness of Normalized P-means for Goods and Chores, and this is joint work with Owen and Alex, all from Purdue University. So this talk is about fair division, and in fair division there are a bunch of agents, and there are some items or resources, and our task is to allocate these items to these agents, and our goal is to do this in a fair and efficient manner. And one fundamental way of doing this allocation is via the use of welfare functions, which is to say that for the case of goods, we take a monotone function of the utilities of the agents and we try to maximize it, and for the case of chores, we take a monotone function of the costs of the agents and we try to minimize it. One natural class of such welfare function is that of the p-mean welfare functions, which are parameterized by the single parameter p and are defined as follows. The reason why they are interesting is because they capture pretty much all of the most prominent welfare notions, like for p equal to 0 Nash welfare, for p equal to 1 social welfare, and so on. So let's look at what is known about welfare functions and fairness in 4 of fair division's fundamental settings. For the case of goods, whether it's divisible or indivisible, it is known that maximizing Nash welfare gives us fair and efficient allocations. For the case of divisible, that means that we get Pareto efficient and envy-free allocations. And for the case of indivisible, we get PO and EF1 allocations. And for both of these settings, it is known that Nash welfare is unique in the sense that for divisible goods, it's the unique rule which satisfies a few fairness axioms, and for indivisible goods, it's the unique welfareist rule which gives EF1 allocations even for 2 agents. And it's also known that other p-means can be terribly unfair. On the other hand, for the case of chores, we know that p-means give no fairness guarantee, whether it's divisible or indivisible. And in fact, in our paper, we established this strong negative result saying that minimizing any monotone welfare function does not give any guarantees, any fairness guarantees, or any approximate fairness guarantees, approximation of proportionality and freeness, prop 1 or EF. So for the case of chores, things are really bad. And for the case of goods, things are good in the sense that like Nash welfare works. So this raises this question that why Nash welfare works and others don't. And an observation here is that only Nash welfare satisfies this key axiom of scale invariance and others don't. So in some sense, Nash welfare is this superpower which makes Nash welfare fair, and other p-mean welfare functions don't have scale invariance and they are unfair. So to fix this, we define this new class of objective function called normalized p-means, which are again parameterized by the single parameter p and defined as follows. So these normalized p-means are scale invariant by design for all p. And importantly, they are not a welfare function because they not only depend on the utilities of the agents, but they also depend on their value for the grand bundle, set of all items. And our goal in the paper is to study the fairness properties of these normalized p-means. And for the case of divisible goods, we show that maximizing normalized p-means for all p less than or equal to 0 gives us PO and proportional allocations, and p greater than 0 is unfair. And for the case of indivisible goods, these fair divisible allocations can be rounded to get PO and prop 1 allocations for all p less than or equal to 0. And for the particular case of 2 agents, we in fact get PO and EF1 allocations for all p less than or equal to 0. And for the case of chores, we show that if we minimize the normalized p means of the costs for p greater than 1, then we get p1 approximately proportional allocations. And similar to the case of goods, we can get indivisible chore allocations by rounding such allocations, divisible allocations. And by rounding the divisible fair allocations, we can get p1 approximately prop1 allocations for p greater than 1. And for the case of two agents, minimizing normalized p means for p greater than or equal to 2 gives us PO and EF1 allocations. So, I mean, normalized p means gives us fair allocations in all these 4 quadrants. So to summarize, normalized p means gives us an infinite class of fair objectives. They are fair for goods, chores, and whether they are divisible or indivisible, and circumvents the uniqueness of Nash because they are not really a welfare function. And finally, I would want to just list a bunch of open problems, that they are open problems related to axiomatic characterizations, other fairness notions, arbitrary entitlement, mixed mana, and other questions. And that would be it. Thank you.
Thank you very much. The next talk is by Aric Fowler. Looks good. But I can't hear you.
There we go. Okay, so my talk is going to be about the score reveal problem, which is a new problem that has yet to be published or researched publicly. So the score reveal problem considers a score matrix of votes. So we have a set of voters, 1 to 4, and they've each ranked 4 different pets, and we want to announce these results. So the result is the final scores of the candidates. And in this case, the cat won. And our aim is we want to announce these votes to a spectator, and we want to maximize the entertainment value of the announcement. So if we announce them one by one, we end up with these intermediate scores of the candidates after each vote is revealed. And we can see that in this case, it's not very interesting because the cat gets an early lead, stays in the lead and wins, and not much else happens. If we reverse the permutation of the voters, we see we get the same outcome, but now it's a more interesting reveal order. So we have the cat sweeping from last place to first place, we have the snake starting in first and coming last, and we have 3 different candidates in first place at different points. So this is a much more interesting ordering of the voters. So to solve this problem, we need to define what entertainment actually is. There is some research in, I think it's economics and consumer behavior science. So suspense and surprise model is based on outcomes and world states. So in our case, our outcomes are the rankings of the candidates, and each world state is at each discrete moment in time, what are the probabilities of each outcome? So they define suspense as a high variance in the set of believed next world states. So if you imagine a football match, if a team is about to shoot for goal, there's a high variance between the outcome if they get the goal and the outcome if they miss. So there's a high variance in the expected next world state. On the contrary, surprise is retrospective, and it says the current world state is highly different to the previous world state. So they use this and they look at tennis. So in this case, we have an interesting game where Federer wins the first 2 sets and then loses the next 2 sets. And then in the final set, it swings from Federer to Djokovic, and we have this really exciting tennis match. And on the flip side, we have the Murray and Nadal semifinal, where Murray just slowly loses until the end of the match where he's lost. So we have a very strong difference in the entertainment of these 2 tennis matches. So part of our research is applying this model to the score reveal problem. So this is one way that we've done this. This is the position shifting measure. And we can count for any given reveal, how many times do the candidates cross over? So if we take all of the intermediate scores, we're counting the number of crosses between their lines. And if we want to maximize this, how can we do that? So this is an optimization problem. We believe it to be NP hard, but we're not entirely sure of that yet. But there's a few other kind of measurements of entertainment that we can compare this with. So for those of you who might have watched Eurovision last weekend, you will be familiar with the lengthy jury vote section. This is the data from 2021. And actually here, 3 votes before the end, the gap between first and second place is so large that the second place candidate can't win anymore. So in the original reveal order from 2021, the outcome was actually resolved before the last vote. So we can fix that by revealing the votes in a different order such that they are closer together towards the end. And that's just one of the ways we can optimize for entertainment. So I realize I have nearly a minute left. So a few of the other entertainment features we're looking at are different measurements of suspense and surprise, considerations for supporters of candidates, and whether their entertainment is dependent on certain candidates, and also the consideration of what I would call irrelevant candidates, i.e. candidates that are very low down in the rankings, and whether they should be ignored in favor of optimizing entertainment for the winning candidates instead. So that's just a brief summary of the score reveal problem research so far, and I hope you enjoyed.
Thank you very much, very entertaining. Our next talk is by Federico Fioravanti.
Can you see my screen? Yes, no?
Not yet, yes.
Now? Yes.
Yeah, now it's good.
Good. Thank you, Dominic. Hello, everyone, and thank you for the space where I can communicate a bit about my research interests. Hopefully, I will encourage some of you to do some research on classification aggregation, what it is. So we can consider the situation of a set of n agents that have to classify a set of n objects into different categories. 2 simple examples can be a set of manager that has to assign different tasks to a set of workers, or a set of culinary experts that has to classify a set of restaurants. What can we find in the literature about this topic? Well, when a category must be filled by at least one object, we have impossibility results, also known as dictatorial results. And one way to avoid this is to consider a fuzzy setting. And this fuzzy setting can be motivated by the next example. So we have a set of n neural networks that have to classify images, which are used to classify different images of dogs, cats, and rabbits. Each neural network tells the degree of confidence that a given image is an image of a dog, a cat, or a rabbit. And then the aggregated classification, of course, is the degree of confidence that a given image is an image of a dog, a cat, or a rabbit. So when we have this, what I call fuzzy setting, we have that the only aggregator that satisfies unanimity and independence, that are 2 classical Saussure-Choles properties, is the weighted arithmetic mean. That is where each neural network or each agent has a different weight, and that weight contributes to the final social classification. So this working paper that you can find in arXiv, where this characterization is shown. And what are my future research directions? Not necessarily working with fuzzy settings, but in general on this classification aggregation. So I want to answer questions like what happens if we drop the condition that a category must be filled by at least one object, or what happens if we allow one object into more than one category. Also, what other settings or properties are interesting for this problem? In particular, it would be nice to find more possibility results. So if any of you is interested on any of these questions, or in anything that is related to the classification aggregation or something known as the group identification problem, I will be happy to discuss about it, or you can drop me an email or whatever you want. I will be happy to talk about it. Okay, thank you for the space.
Thank you very much. Our next talk is by Tian Yu.
All right. Hi, my name's Tian. I'm a fourth-year PhD student in the Department of Economics at Texas A&M. And this project doesn't exactly fall under computational social choice, but I hope you can enjoy this talk about instant runoff voting anyways. So there's been growing support in the US for the implementation of voting rules other than plurality. This, of course, begs the question, how should we pick an alternative voting rule? Traditionally, we've approached this question axiomatically, but how about in situations where different voting rules would result in the same outcome? Do different voting rules still generate meaningful differences in other electoral outcomes that we might care about, such as voter participation? And that's exactly my research question. So, is there an effect of instant runoff voting on participation if we hold electoral outcomes constant? In order to answer this question, I also want to address a broader methodological issue, which is how should we evaluate voting rules empirically? So existing research can kind of be classified into three categories. So studies that use observational data, simulations, or lab experiments. These methods all have their pros and cons, but I would argue that maybe the ideal method would be a field experiment using real elections. So during an election year, randomly assigning voting rules across the United States and seeing what happens. Of course, that's not possible, right? But I think we can get pretty close by using voting contests in the field with consequential outcomes. And that's exactly what I do. Because I want to draw parallels to political elections, the candidates I use are charities. I think charities provide a good proxy for political candidates because you can kind of view them as single issue candidates. And so that's what I do. I advertise elections to Texas A&M students as a charity fundraising initiative. And so I send out emails that basically say, hey, in the following few weeks, I'm going to be holding a series of voting contests to raise money and bring awareness to charities. If you click this link, you can vote for your favorite charity, and the winning charity is going to receive $500. So when students click the link, they are randomly assigned to different elections that use different voting rules. This environment is nice because it also provides a natural setting where voters aren't really aware that they're kind of subjects and kind of under scrutiny. And so my unit of observation here is the rate of return to subsequent elections, as well as answers to survey questions at the beginning and end of elections. Okay, so in order to implement these proxies for real elections, I follow a three-step process. So first, I conduct a calibration survey to get the distribution of charity and political preferences. Then I use this data to simulate elections in order to guarantee to calibrate elections where they're going to result in the same winner. And then I run these elections. And so the one result I want to talk about is from the calibration survey. So in this calibration survey, one, I need to get data to simulate the elections. But another reason why I do this calibration survey is to confirm that charities make a good proxy for political candidates, right? I want to see that the distribution of support for charities is the same as the distribution of support for same as the political distribution, right? And so I elicit political preferences in two ways and charity preferences in three different ways. And these results are robust using any combination of these elicitation techniques. And so what you see here is the distribution of support for charities that I would consider neutral ex ante. And so clearly you can see there's not really any differences between the levels of support of Democratic participants and Republican participants. Here, I'm showing the differences in levels of support for liberal charities, and you can clearly see that there is a difference here, and the same for conservative charities. And so that's all the time for today. Thank you.
Thank you very much. The next talk is by Somyajit Pine.
Hi, can you hear me?
Yep.
Yeah, okay. So let's start. So my name is Somyajit. I'm a third-year PhD student from TFL Mumbai, and this is a joint work with Umang Bhaskar. So so let's start with an example where the voters are distributed in the interval 0, 1 according to a bounded density function fx. There are two candidates placed on positions x1 and x2, and the voters vote for the closest candidate. That means that the voters in the red region vote for the red candidate and the voters in the blue region vote for the blue candidate. And we call a strategy profile an equilibrium if no candidate can strictly increase their vote by moving to a difference location. And clearly this is not an equilibrium because the red candidate can move closer to the blue candidate like this and can increase his vote share. So we have an assumption in our model that is the distance between any two candidates is at least delta, which is also called minimum differentiation in Hoteling's model. So what is an equilibrium in for two candidates? So let's say mu is a median, and we place the candidates like this. Then each of the candidate is getting almost 50% of the vote, and no one can increase their vote share by deviating to another location. So for two candidates, there is always an equilibrium. What about three candidates? So for three candidates, let's say they are placed like this, x1, x2, and x3. And this is not an equilibrium because the red and the green candidate will try to go closer to the blue candidate like this. And now the blue candidate is getting nothing. Okay, so it will try to deviate to another location. So this is not an equilibrium also. And it turns out for three candidates, there is never an equilibrium for any distribution. Okay, so now let's talk about additive approximate equilibrium. So let's say the voters are distributed according to this piecewise linear function where these numbers are the voter masses. And you can check that no candidate can increase its vote share by more than 1/8 by more than 1/8, and that's why it's a 1/8 additive approximate equilibrium. So formally, a strategy profile is a epsilon additive equilibrium if no candidate can increase his vote share by more than epsilon by deviating to a different location. So the problem we want to address is, given a distribution of the voters and m candidates, what is the smallest epsilon approximate equilibrium we can achieve? So now why the approximate equilibrium is interesting. So it'll show that generally this model does not admit an equilibrium. But the absence does not provide much information if one can approach very close to an equilibrium. Equivalently speaking, how stable the model is, we don't know. But the approximate equilibria provide a good insight into the stability. Also in practical application, approximate equilibria is commonly, equilibria are commonly studied because the exact equilibria either do not exist or, hard to find, okay, or compute, you can say. So what are our results? So for three candidates, we know that there is no equilibrium. So the epsilon is strictly greater than 0. Then the natural question should be, what is the lower bound? And we showed that the lower bound is 1/12. And this is surprising because, now we can show, so this means that some candidate can always increase his vote by at least 8.5%. And this bound is also tight. That means that there exists a distribution where you can actually achieve 1/12 approximate equilibrium. Now, what are some algorithmic guarantees? So we have given an algorithm, polytem algorithm, that gives you a 1/6 approximate equilibrium for any distribution of the voters. And this bound is also tight. That means there exists a distribution where you cannot do better than 1/6. And this is a corollary from a general theorem that I will state in the next slide. So we have given a polytem algorithm for m candidate also that gives you 1/m+1 equilibrium. And so this algorithm is very simple. It just places the candidates on the n+1th quantiles. So here we also have shown a lower bound that is 1 by n+3. That means that there exists a distribution where you cannot obtain better than a 1 by n+3 equilibrium, approximate equilibrium. So now if you put m equal to 3, it becomes 1 by 6. That was our last result that we have shown in the last slide. So now what are some open questions we can say? So there is a gap between our bounds, right? So the upper bound is 1 by n+1, the lower bound is 1 by n+3. So it will be very interesting if someone can close the bound. And the other question is, can we extend this model to general dimensions? So let's say the voters are now distributed on a plane and the candidates are choosing their positions accordingly to maximize their vote share. So this is it. And we have worked on a different variant also. If someone is interested, we can talk about it in the breakout room. So thank you, everyone.
Thank you very much. And our next talk is by Vasilis Christoforidis.
Yeah.
Perfect.
Can you? Oh, okay, great. Yeah. Hi, everyone. I'm Vasilis. And I'll be presenting joint work with Christos Adodneos. That's going to appear in NightSky this summer. And Christos is also in the chat to answer any questions that you might have. So we focus on the fundamental problem of allocating indivisible items among a set of agents. So we have a set of n agents, and we focus on the case of indivisible chores, where we have to allocate a set of n chores. Each agent I has a cost function Ci, which specifies the cost that she might have for a bundle of items. And it's a well-known fact that MV3 allocations might not exist for indivisible items. And EFX, MV3ness up to any item, is regarded as the most compelling fairness notion in this context. And the definition for chores dictates that whenever agent I ends agent J, the env is eliminated after the hypothetical removal of any item from agent I's bundle, so reducing the env. So MV3ness up to any item was formally defined by Karagiannis, Kudokava, Mglam, Prakash, Simon Wang back in 2016. And since then, it has attracted significant attention in the area, and it's a major problem, has been even deemed as Fair Division's biggest problem by Aric Prakash. And despite the fruitful agenda and the many results that we know, there still remains a big gap in understanding the notion. So most of the results applied only to special cases or in restricted settings. And moreover, the landscape of EFX allocations is even less explored in the context of chores. So many people have speculated that it might be easier to, at least for general evaluations, to construct a counterexam. And indeed, we saw that this is the case for chores. We saw that an EFX allocation for chores might not exist at the general cost functions, and we present a single construction with only 3 agents and 6 chores, in which no EFX allocations exist. So we know that no such counterexam was known under any subset of general monotone functions, either for goods only or chores only. And the only known counterexams were in the mixed mana setting, where we have mixtures of goods and chores. And this already establishes a separation result with a goods counterpart, where we know that EFX allocations always exist for 3 agents and 6 goods due to Mahar, even under general monotone variations. So obviously I don't have the time to go into full detail, but I want to highlight the fact that it's a particularly simple construction where we have 3 agents and 6 chores. All of the agents serve the same values for singletons, for single items. So the ones you can see here. And we have agents A and items A and items B. And we call items B the special items, and particularly B1 is more special to agent 1, B2 is more special to agent 2, and etc. And there's a special structure. We employ super additive cost functions. And let's say when B1 is bundled with either one of those items from A, then the cost for agent 1 goes to infinity, or let's say to a very large number, while also when B2 is bundled together with B3, his value also goes, his cost also goes to infinity. So we can show that no agent can receive 2 or 3 special items. So it remains to check what happens when, let's say, we shuffle the special items and allocate each agent 1 B item. Then the problem actually reduced to finding an MV3 allocation of the last remaining items, and that's what shows that no allocation exists. So one might wonder what happens with approximations. We also saw that this is not possible. Our construction, in fact, shows that no approximate solution exists for any approximation factor. Moreover, determining whether the instance admits an effects allocation is NP-complete. And we further saw some positive results regarding a setting with few items, and also some improved approximations for 3 additive agents and some conditional approximations. Thank you.
Thank you very much. And thanks to all the speakers. Now is the time for our second discussion session. So please stick around for the next 10 minutes and speak to all the speakers you have questions for.